Good morning. This is an audio recording for visually impaired student. Today I am going to read a chapter named Phenol from Modern Organic Chemistry written by Dr. J.M. Shegel. Introduction. Phenol are aromatic hydroxy compound in which the hydroxyl group is directly attached to an aromatic ring. They may be represented by the general formula AROH, where AR represent a phenyl, a substituted phenyl or some other aryl group such as naphthyl. Depending upon the number of hydroxyl group attached to the aromatic ring, the phenol may be classified as mono, di, trihydric phenol and so on. For example, we have monohydric, dihydric, trihydric, etc. The hydroxyl group attached to the aromatic ring is known as phenolic group. As already stated in chapter 3, phenol are different from aromatic hydroxy compound in which the hydroxyl group is present in the side chain. The latter type of compound are in fact aryl substituted aliphatic alcohol and their behavior is similar to that of aliphatic alcohol. However, both phenol and aromatic alcohol resemble each other in undergoing the electrophilic aromatic substitution and in certain other respects. Nomenclature of phenol. The simplest member of phenol is always known by its popular name phenol, although its IUPAC name is benzoyl. All substituted monohydric phenol are named as derivative of the simplest member of the series, example phenol. However, methylphenol possesses special common name. The position of substituent with respect to OH group are denoted by O, M and P in the common system, but by the number in the IPX system with the OH carrying the number 1. The following example illustrate the method of naming phenol. The name given in bracket are their common name. Phenol, 2-chlorophenol, 2,4-dinitrophenol, 2-methylphenol, 3-methylphenol, 4-methylphenol. Di and trihydric phenol have the IUPAC name benzene diol and benzene triol respectively, but most of them are known by their special name as given below. 1,2-benzene diol called 1,2-dihydroxybenzene. 1,3-benzene diol called 1,3-dihydroxybenzene. 1,4-benzene diol called 1,4-dihydroxybenzene. 1,2,3 benzene triol called 1,2,3 trihydroxybenzene. 1,3,5 benzene triol called 1,3,5 trihydroxybenzene. It should be noted, however, then when a compound contains some functional group such carboxylic group, ester or carbonyl group in addition to phenolic group, the compound is named as hydroxy derivative of the acid, ester or carbonyl compound. For example, 4-hydroxybenzyl aldehyde, 2,4-dihydroxybenzoic acid, ethyl 4-hydroxybenzenoate. Structure and bonding. Phenol are compound having a hydroxyl group directly bonded to benzene ring, while oxygen of hydroxyl group is in sp3 hybridized state. The carbon of the benzene ring to which oxygen is bonded is in sp2 hybridized state. Resonance interaction take place between a lone pair of electron on oxygen and the benzene ring so that phenol exists as resonance hybrid of resonating structure. Due to resonance, the carbon-oxygen bond acquires some double bond character and becoming shorter and stronger than the carbon-oxygen bond in alcohol. At the same time, oxygen acquires a slight positive charge due to which it attracts the electron pair OH bond strongly toward itself. As a result, the OH bond in phenol became more polar than in alcohol. Due to above structural feature, phenol behave differently from alcohol in many respects. So they are treated as a separate class of compound. Method of formation. The commonly employed general method of preparation of phenol are discussed below. First, hydrolysis of diazonium salt. This is probably the most convenient method of preparation of phenol. The reaction is usually carried out by slowly addition diazonium salt solution to excess boiling dilute sulfuric acid. Benzene diazonium chloride react with water to form phenol plus HCl plus N2. Since hydrolysis is carried out under very mild condition, other group in the molecule of diazonium salt are not affected. M-nitrobenzene diazonium hydrogen sulfate in presence of water, it will give M-nitrophenol plus H2SO4 plus N2. Second, alkali fusion of sulfonates. In this method, phenol are obtained by fusion of sodium salt of aromatic sulfonic acid with sodium hydroxide followed by acidification. Sodium sulfonate plus 2 mole of NaOH, it will give aromatic ONA. In presence of HCl, it will form phenol plus NaCl. This method cannot be applied to salt of sulfonic acid containing substituent such as chlorine, NO2, COOH due to the possibility of various side salt reactions. Third, from isopropyl benzene called cumene. This method is used particularly for the large scale preparation of phenol from isopropyl benzene, popularly known as cumene. Cumene is readily oxidized by air to form cumene hydroperoxide, which is converted into phenol and acetone by treatment with an aqueous acid. Cumene in presence of air at 333 to 353, it will give cumene hydroperoxide, and with the hydrolysis it will form phenol plus acetone. Mechanism. The mechanism of conversion of cumene hydroperoxide into phenol involves the series of 5 steps as shown in figure. First is a step of addition of H positive. Second is the removal of water. Third is phenyl shift. Fourth is addition of water. Last but not least is the removal of H positive ion. In step first, peroxide get converted into a protonated peroxide from which a water molecule is eliminated. Step 2, to form an intermediate having electron deficient oxygen. In step 3, 1-2 shift of the phenyl group take place giving a carbocation which is resonance hybrid of two structure. The carbocation take up a molecule of water. Step 4, to form a hemiacetal. The hemiacetal finally break. Step 5, to yield phenol and acetone. It may be noted that cumene itself is obtained by Friedel-Crafts reaction between benzene and propylene in the presence of ferric chloride. Fourth, from aryl halide, substituted phenol having electron withdrawing group like an auto group in ortho-para position to the OH group can be easily prepared from the corresponding aryl halide by treatment with aqueous sodium hydroxide. For example, P-nitrochlorobenzene in presence of 2 mole of NaOH give salt of phenol, salt of Na. After that, in the presence of HCl, it will form P-nitrophenol. Phenol itself is also manufactured by this method by heating chlorobenzene with 10% sodium hydroxide solution at 603 to 623 Kelvin under a pressure of 200 atmosphere in the presence of copper salt. This process is known as Dow's process. Fifth, from phenolic acid. Distillation of sodium salt of phenolic acid with soda lime yield phenol. For example, sodium salicylate with NaOH, it will form phenol plus Na2CO3. Sixth, from Grignard reagent. Phenol may be prepared by treatment aryl magnesium bromide with oxygen followed by hydrolysis of the product. Phenyl magnesium bromide in the presence of oxygen give 2 mole of benzene OMgBr. In presence of H3O positive, it will form phenol plus 2 mole of MgOHBr. 7 from coal tar. Phenol and aerosols are also obtained on a large scale from the middle oil fraction obtained on the distillation of the coal tar. Physical property. First, physical state. Pure phenols are generally colorless liquid or solid, but they usually appear slightly colored as they readily get oxidized even in air, and the oxidation product are color compound. At the same time, substituent like NO2 also impart color to phenol. Second is the boiling point. Due to the formation of intermolecular hydrogen bonding, phenol considerably higher than corresponding hydrocarbon and aryl halide which do not contain hydrogen bond. For example, phenol with molar weight 94 boil at 455 Kelvin, while toluene with molar weight 92 boil at 384 Kelvin. Third is a solubility. Phenol are practically insoluble in water, although phenol itself and some di and trihydric phenol are fairly soluble. The solubility of these compounds is probably due to the formation of hydrogen bond with water. But the extent of hydrogen bond formation is very small due to the large size of the phenyl group, which masks the polar character of OH group. All phenol are soluble in aqueous alkaline solution due to the formation of water soluble salt. Phenol containing substituents such as NO2 can also form intramolecular hydrogen bond. This is responsible for certain interesting observation. For example, O-nitrophenol has a lower boiling point and smaller solubility in water than its meta or para isomers. This is because the ortho isomers form intrahydrogen bond between oxygen of nitrogen group and the hydrogen of hydroxyl group. This phenomena is known as chelation. Greek chili means claw. Due to intramolecular hydrogen bond or chelation, the ortho isomers has only very small tendency to form intermolecular hydrogen bond. On the other hand, in the meta and para isomers, the hydroxyl and nitro group are so situated that intramolecular hydrogen bonding is not possible while intermolecular hydrogen bonding take place. Chemical property. Phenol are highly reactive compound which combine the reaction of both the hydroxyl group and aromatic ring. The important reaction of phenol are discussed below. First, reaction of phenolic group. First is a acidity. Phenol are weakly acidic compound. They react with aqueous alkali metal hydroxide to form salt known as phenoxides. However, phenol do not react with aqueous carbonate or bicarbonate. Moreover, the salt of phenol are converted into phenol by aqueous mineral acid, carboxylic acid or even carbonic acid. These observations indicate that phenol are very weak acid, weaker than carboxylic acid or even carbonic acid. This is confirmed by the comparison of their acidity constant Ka or pKa value. While phenol have Ka value of order 10 raised to the power minus 10, carboxylic group and carbonyl group have K value of 10 ki power minus 5 to 10 ki power minus 7 respectively. These days, acidic strength are usually represented in the term of pKa value, which is negative algorithm of acidity constant. That is, pK is equal to minus log of Ka. For example, pK of phenol is 9.88. It may be noted that stronger acid has larger Ka value but smaller pK value, but a weak acid has smaller Ka value but larger pKa value. Even though very weakly acidic themselves, phenol are much more acidic than alcohol, which have Ka value of order 10 raised to the power minus 16 to 10 raised to the power minus 18. This appears to be rather surprising since both phenol and alcohol are characteristics by the presence of hydroxyl group. What then is the reason that an OH attached to an aromatic ring is so much more acidic than an OH attached to an alkyl group? We should attempt to answer this question by considering the stability of the ion formed relative to the stability of unionized compound. Explanation of acidic character. Ionization of phenol is an equilibrium reaction involving the unionized phenol and phenoxide and hydronium ion as follows. C6H5OH plus water, it will give C6H5O negative plus H3O positive. Now, neither phenol nor phenoxide ion can be represented by only one valence bond formula. On the other hand, each of them is a resonance hybrid of various contributing structures, as shown below. It may be noted that contributing structure IC-ID-IE of phenol involving separation of charge and are therefore less stable than the structure IA and IB. On the other hand, in the case of phenoxide ion, none of the contributing structure involving charge separation and the structures are almost equally stable. As such, phenoxide ion is resonance stabilized to a great extent than phenol. Therefore, the equilibrium between phenol and phenoxide ion favored the formation of phenoxide ion and the hydronium ion. This account for the acidic character of phenol. Comparison with alcohol. In case of alcohol, equilibrium reaction involve alcohol and alkoxide ion does not favor the formation of alkoxide ion and hydronium ion. This is because there is no resonance stabilization of alkoxide ion relative to alcohol, since neither the alcohol nor the alkoxide ion exhibit resonance. That is ROH plus water, it will form RO negative plus H3O positive. And hence it should not be surprising that compared to alcohol, phenol ionizes more readily to form phenoxide ion and hydronium ion. In other words, phenol are more acidic than alcohol. Effect of substituent on the acidity of phenol. The acidity of phenol is strongly influenced by the substituent attached to the benching ring and their position. This is because the state of equilibrium in the reaction between phenol and water to furnish phenoxide ion and the hydronium ion depend upon the stability of the product relative to the stability of the reactant. Any factor which stabilizes the phenoxide ion more than the parent phenol should increase the acidity, while any factor that destabilizes the phenoxide ion should decrease the acidity as illustrated below. First, is the nature of substituent on the benching ring. A. Electron withdrawing substituent. Phenol having electron withdrawing substituent, each has halogens and nitro group are more acidic than phenol itself. This is because an electron withdrawing substituent attract the electron toward itself, thus disperse the negative charge of the phenoxide ion. As a result, it stabilizes the phenoxide ion and increase the acidity of phenol. B is electron releasing substituent. Phenol contain electron releasing group such as alkyl group are less acidic than phenol itself. This is because an electron releasing substituent release the electron away from itself and thus intensify the negative charge on the phenoxide ion. In this way, it destabilizes the anion and thereby decreases the acidity of the phenol. In short, electron withdrawing group increase the acidity of phenol while electron releasing group decreases their acidity. Second is the position of substituent related to hydroxyl group. Apart from the nature of substituent, the position of the substituent relative to hydroxyl group also has large influence on the acidity of the phenol. This may be explained as follows. First, the stabilizing or destabilizing influence of the substituent operates through inductive effect as well as the resonance effect. Second, the intensity of inductive effect of the substituent decreases at its distance from OH group increases. That is ortho position greater than meta position greater than para position. Third, the resonance effect is more pronounced if the substituent is in ortho or para position than in meta. To understand this, let us examine the contributing structure of ortho, meta, and para nitrophenoxide ions. It may be seen that each of O and P nitrophenoxide ion is a resonance hybrid of 5 contributing structure. In one of the structure in each case, the structure marked star, conjugation is extend up to oxygen atom of the nitro group. But no such conjugation is possible for M nitrophenoxide ion and has only 4 contributing structure. The net result is that there is great resonance stabilization in ortho and para anion than the meta isomers. As such, ortho and para nitrophenol are much stronger acid than meta nitrophenol. An interesting observation is that certain phenol having electron withdrawing group in the ortho position are weaker than para isomers. For example, O-fluorophenol is a weaker acid than P-fluorophenol and O-nitrophenol is a weaker acid than P-nitrophenol. This can be attributed to the formation of intramolecular hydrogen bond. Second is ether formation called the Williams synthesis process. On reaction with alkyl halide or dialkyl sulfates in alkyne medium, phenol are converted into corresponding alkyl ethers. The alkyl halide or sulfates undergo nucleophilic substitution by the phenoxide ion present in alkyne solution of phenol. Thus we have AROH plus NaOH, it will give ARO negative Na positive plus water. ARO negative plus Rx, it will give AROR plus X negative. ARO negative plus ROSO2OR called dialkyl sulfide, it will form AROR plus alkyl sulfate ion. Cleanson rearrangement. This is an interesting rearrangement reaction involving aryl allyl ether. When heated at 575 Kelvin, the allyl group of the ether migrate from ether oxygen to the ring carbon at ortho position. If both the ortho position are already occupied, the alkyl group migrate to para position. For example, allyl 2,6-dimethylphenyl ether at 475 Kelvin, it will form 4-allyl 2,6-dimethylphenol. Mechanism of ortho rearrangement. Orthoisomerism involving a concerned mechanism in which the cleavage of allyl oxygen bond is chronized with the formation of allyl carbon bond at ortho position. The cyclohexadione intermediate thus formed undergoes a tautomeric change to give O allyl phenol in which ring regain the aromatic character. It may be useful noted that there is an alpha carbon of the allyl group with respect to oxygen which attaches itself to the ring carbon. This is spotted by the fact that orthomigration involving an inversion in the position of substituent in the allyl group with respect to that of the starting compound. Mechanism of para rearrangement. Para isomerism involving two stages. In the first stage, orthomigration takes place and the cyclohexadione intermediate is formed. But this intermediate cannot undergo tautomerism since there is no hydrogen at ortho position as both these positions are already substituted. As such, these intermediate undergo another migration of alkyl group, ultimately yield the final product. It may be noted that in para-isomerism, two migrations take place, each of which accompanied by inversion. In the other word, one inversion is followed by another inversion so that there is no net inversion in the position of the substituent with respect to the starting compound. Third is the ester formation called acylation. Like alcohol, phenol are converted into ester by reaction with carboxylic acid, acid chloride or acid anhydride. However, in actual practice, esterification is better carried out by the use of acid chloride or anhydride in presence of either an acid or a base such as pyridine. Phenol react with acid chloride in presence of pyridine to form phenyl propenoate. Phenol in the presence of acid anhydride in presence of pyridine, it will form phenyl acetate. Benzylization of phenol is usually carried out in the presence of aqueous NaOH. Since benzoyl chloride is not easily hydrolyzed by alkyls, the reaction is called Schottenhahn-Baumann reaction. Mechanism. To start with alkali attack the phenol to form phenoxide anion. These anions undergo nucleophilic attack on the carbonyl carbon of an acid chloride to form tetrahedral intermediate. The intermediate then lose a chloride ion to form the ester. Fries rearrangement. If an ester of a phenol is heated with aluminium chloride, the acyl group migrate from the phenolic oxygen to the ortho or para position on the ring. This is called Fries rearrangement. For example, phenyl propanoate at 413 to 423 Kelvin in the presence of AlCl3 form 50% of p hydroxy phenyl ethyl ketone and 35% of ortho-hydroxyphenyl ethyl ketone. At low temperature, para product predominate while at high temperature orthoisomer is main product. Mechanism. The rearrangement probably involved the formation of an acylium ion which then attack the aromatic ring as in Friedel-Crafts acylation. The complete mechanism may summed up as follows. Fourth, reaction with zinc dust. When distilled with zinc dust, phenol form corresponding hydrocarbon. For example, phenol with zinc in the presence of heat, it will form benzene plus ZNO. Fifth, reaction with ammonia. When heated with ammonia at high temperature and pressure, the presence of catalyst like anhydrous zinc chloride OH group of phenol is replaced by NH2 group. For example, phenol plus NH3 in the presence of anhydrous ZnCl2, it will form benzene with NH2 plus water. Reaction of aromatic ring electrophilic substitution. Phenol readily undergo electrophilic aromatic substitution reaction. The OH group linked to an aromatic ring activate the ring to electrophilic substitution and direct the incoming group to ortho and para position. In fact, the OH group is very powerful activator and unless precautions are taken, poly substitution take place. Explanation of ortho-para directing and activating influence of OH group toward electrophilic substitution. The ortho-para directing and activating influence of OH group toward electrophilic aromatic substitution can be explained in terms of assumption that oxygen of this group can share more than one pair of electron with the ring due to resonance. When phenol undergo electrophilic substitution, the contributing structure of intermediate carbocation formed by the attack of electrophile says is positive. At ortho, para and meta position are shown below. The carbocation formed by ortho attack is a resonance hybrid of four structures, third A to third D. Of these four structures, the structure third D is particularly stable since in it each atom has complete octet of electron. Similarly, in para attack, the carbocation is a resonance hybrid of four structure, fourth A to fourth D, of which fourth D is more stable. But in case of meta attack, the carbocation is a hybrid of only three structure, fifth A to fifth C. There be no structure corresponding to third D to fourth D. This means that the positive charge of the ortho and para anion is dispersed over more than is that of the meta ion. It is therefore parent that the hybrid carbocation resulting from ortho and para attack are more stable than the carbocation resulting from the meta attack or from the attack on benching itself. Thus, substitution in phenol occur mostly at ortho and para position and occur at a faster rate than in case of benzene. The important electrophilic substitution reaction of phenol are discussed below. Sixth is the halogenation. On treatment with halogen, phenol are very rapidly halogenating, forming polyhalogen derivative. For example, reaction of phenol with an aqueous solution of bromine immediately produces a precipitate of tribromophenol. In fact, the reactivity of phenol toward halogenation is so great that even substituent like SO3H group, if present in ortho or para position, get displaced. Halogenation can, however, be limited to monohalogenation stage by performing it at low temperature and in non-polar solvent such as carbon tetrachloride or carbon disulfide. For example, phenol plus bromine in presence of CS2, it will form P-bromophenol plus O-bromophenol plus HBr. The above observation can be explained in terms of fact that the greater the electron density around benzene ring, the more easily it undergo electrophilic substitution reaction. In aqueous solution, phenol ionized to form phenoxide ion. Due to the presence of negative charge on it, oxygen of the phenoxide ion release electron toward the benzene ring to a large extent. As a result, electron density around benzene ring become very large so that the ring is highly activated and undergoes tri-substitution. In non-polar solvent such as CS2, phenol does not undergo ionization to an appreciable extent and occur mainly as unionized molecule. The OH group of phenol can release electron toward benzene ring only to a small extent. As a result, benzene ring is not strongly activated and therefore it undergoes only mono substitution reaction. Seventh is nitration. Nitration of phenol give poor yield of the expected nitro compounds. This is because phenol are easily oxidized and nitric acid can bring about not only nitration but also oxidation of starting phenol. Phenol with dilute HNO3 at 298 Kelvin, it will form 40% of orthonitrophenol and 13% of p-nitrophenol. Use of concentrated nitric acid in the above reaction lead to the formation of 2,4,6 tri-nitrophenol or picric acid in low yield. Eighth is sulfonation. Sulfonation of phenol proceed readily to yield either the ortho or a para isomer as the main product depending upon the temperature of the reaction. In general, low temperature favor the formation of ortho isomers while high temperature favor the para isomers. On heating to 373 Kelvin, O-phenol sulfonic acid changes to the thermodynamically more stable P-phenol sulfonic acid. 9. Fiddlecraft alkylation. Phenol undergo Fiddlecraft alkylation, forming predominantly para isomers. The reaction is carried out in the presence of HF. Normally, Fiddlecraft reaction is carried out in presence of anhydrous AlCl3. But in case of phenol, these catalyst is not used. This is because electron deficient aluminium atom of AlCl3 coordinate with a lone pair of electron on the oxygen of OH group to form a complex. These suppress the activating influence of OH group so that the yield of the product is very poor. 10th is Fiddlecraft acylation. Phenol can also undergo Fiddlecraft acylation to form ortho and para hydroxyketone by treatment with acid chloride and acid anhydride. But the hydroxyketone are generally prepared by Fry's rearrangement. If 11 is Gattesman's synthesis. When treated with a mixture of hydrogen cyanide and hydrogen chloride in the presence of anhydrous aluminium chloride, phenol give phenolic aldehyde. The reaction known as Gattesman synthesis. constituent an important method for synthesis phenolic aldehyde. For example, phenol in the presence of HCN plus HCl AlCl3, it will form an phenol with aldehyde. The aldehyde group get attached preferably at para position. Mechanism. Getamin synthesis is an electrophilic aromatic substitution in which attacking reagent is formal D-neoyne formed from HCN and HCl in the presence of anhydrous. The complete mechanism may be summed up as follows. 12th, Hoban-House reaction. This is an isolation reaction of polyhydric phenol having hydroxyl group in meta position with each other. It is carried out by treatment such phenol with alkyl cyanide and hydrogen chloride in presence of anhydrous zinc chloride or aluminum chloride followed by the hydrolysis. Mechanism. The mechanism of the reaction is similar to that of the Getesman's reaction. Special reaction of phenols. 13 is a coupling with diazonium salt. When treated with diazonium salt is weakly alkaline solution with pH 9 to 10. Phenol undergo coupling to form hydroxyazo compound. For example, benzene diazonium chloride with phenol give p hydroxybenzene plus HCl. 14 is Kolbe reaction called Kolbe-Sidmid reaction. Carboxylation. When heated with carbon dioxide under pressure, sodium salt of phenol undergo carboxylation to form salt of phenolic acid. The orthoisomers being the main product. For example, when sodium phenoxide is heated with carbon dioxide under pressure, sodium salicylate is obtained as a major product. Mechanism. The mechanism of Kolbe reaction is believed to involve the electrophilic attack on carbon dioxide on the phenoxide ion as shown below. 15. Riemann-Tiemann reaction. On heating with chloroform and an alkali, phenol are converted into phenolic aldehyde and aldehyde group being introduced onto the aromatic ring, generally at ortho position to the OH group. For example, when phenol is heated with chloroform and aqueous sodium hydroxide, salicylic aldehyde is obtained as the main product, along with a small amount of para product. Phenol plus CHCl3 plus 3 mol of NaOH at 3332 to 343 Kelvin, it will form salicylic aldehyde as a main product plus 3 mol of NaCl plus 2 mol of H2O. Mechanism. The mechanism of reaction involves the electrophilic substitution of phenoxide ion formed in solution by the action of alkali on phenol. The attacking electrophilic reagent is the electron deficient dichloromethylene CCl2 a carbene generating by the action of alkyl on chloroform. Dichloromethyl is electrically neutral but it acts as an electrophile reagent as the carbon atom present in it surrounded by only 6 valence electron. The complete mechanism may be given below. If carbon tetrachloride is used in place of chloroform in Riemann-Tiemann reaction, phenol gives rise to phenolic acid. 16. Lender-Mannens reaction. Phenol undergo condensation with aldehyde in presence of an acid or base as a catalyst. The product initially formed get polymerized to form commercially important polymer. For instances, when phenol is treated with formaldehyde in the presence of an acid or alkali, a mixture of ortho and para hydroxybenzyl alcohols was obtained. Phenol plus formaldehyde, it will form ortho and para hydroxybenzyl alcohol. The alcohol formed undergo polymerization to form a resinous polymer called bakelite. Mechanism of initial condensation. The initial reaction between phenol and formaldehyde involved the electrophilic attack of formaldehyde on phenoxide ion called alkaline medium or protonating formaldehyde on phenol called acidic medium. Acid catalyst CH2 double bond O plus H positive. It will convert into the protonated formaldehyde. After that, it will attack on phenol to give phenol with CH2OH. And similar reaction for the base catalyzed. 17. Phthalate reaction. On heating with phthalic anhydride in the presence of concentrated sulfuric acid or anhydrous zinc chloride, phenol are converted into phthalenes. For example, phenol forms phenolphthalein as shown in figure. 2 mole of phenol mixed with acid anhydride to give phenolphthalein. Phenolphthalein is used as an indicator in acid alkali titration. It is colorless in acidic medium but changes to pink color in alkaline medium. 18. Reaction with ferric chloride. Phenol give a violet colorization with ferric chloride due to the formation of water-soluble complex ferric phenoxide C6H5O thrice Fe. Other phenol also formed colored complex green, blue, violet or red on treatment with ferric chloride. The reaction is used as an important test in the identification of phenol. This test is not given by alcohol. 19 is Lieberman reaction. On treatment with sodium nitrite dissolved in concentrated sulfuric acid, phenol give a red color. The color changes to blue on addition of aqueous sodium hydroxide. The reaction is called Lieberman reaction. Thank you.